So the next section is to talk about complex numbers. A lot of this comes down to dealing with solutions to polynomial equations where you have to take the square root of a negative number. So you can here see the example. If you had the polynomial x squared plus 1, then if you went to solve for x, you'd subtract 1 from both sides, take the square root, and you'd have this plus or minus the square root of negative 1, which is not a real number because you can't have the negative argument of the square root. But if we define this new quantity I as equal to the square root of negative 1, then we can come up with solutions, and they involve using imaginary numbers. So imaginary numbers are ones that have the square root of a negative number. Now, one interesting thing about this letter I, if you square I, you square negative 1, which turns out to be anything squared. Square root of anything squared is the argument. So squaring a imaginary number gives you a real number. So that's one of the properties that we'll use a lot. So complex numbers consist of a real part and an imaginary part. We typically say the real part is A, which is a real number. And then we have B, which is also a real number. And then we have I, which is defined as the square root of negative 1. So when you add two complex numbers together, you add the real parts together to get the real part of the answer, and you add the coefficients of the imaginary part and make that the coefficient of the resulting addition added. So adding two complex numbers gives you a new complex number. Now if you're subtracting, again, what you do is you take the real parts, A and C in this case, and you subtract C from A. That's your real part of the answer, the result of this subtraction. And then the imaginary part, you take the coefficient of the imaginary part. The second one that you're subtracting, is subtract that from the first part. So we get B minus D, which again, these are real numbers, times the imaginary, the square root of negative 1, which we call I. Now when you multiply them, you still do the same thing. You're basically using FOIL. In this case, what we're doing is we're taking A, the real part of the first complex number, and multiplying by the two parts of the real and the imaginary part of the second complex number. So we take A times C plus DI, and then we take the second part, the imaginary part of the first complex number, and multiply that by C plus DI. So then if you use the distributive property, you get A times C plus, well, then you have, so that's the real, that's a real number. A real number times a real number is a real number. You also have over here, you have BI times DI. So you get B times D, and I times I is negative 1. So that's where this comes from. The negative comes from I times I, which is I squared. And we said I squared is negative 1. And then you have B times D. Now, the other parts are the imaginary parts, because you've got A times DI, or AD times I, and then you've got BI times C. So you get B times C times I, but you can factor out the I. So both of these are, both AD and BC are multiplied together, and they have a common term, I. So the product has a real part and an imaginary part. You can also use FOIL if you think about it. A times FOIL is first, A times C, and then last, which is BI times DI, which gives you negative BD, and then the inner, well, the outer in this case, and the inner give you the imaginary parts. Now there's a special case where if you take a complex number with coefficients a plus bi, if you change the sign of the complex part from plus to minus, or if it was a minus bi, we change it from minus to plus, these have interesting properties which we'll use. So let's just do an example here. So let's say we have 2 plus 3i. So that's my complex number. The complex conjugate would be 2 minus 3i. And then to do the product, multiplying a complex number by its complex conjugate, if you do first, you'll get 2 times 2. If you do last, you'll get negative 3 times I squared. If you do inner, you'll have 2 times 3i, and then outer will be negative 2 times 3i. So these cancel out. The imaginary parts cancel out. This part, I squared, is equal to negative 1. So we'll get 4. 2 times 2 is 4. We'll get negative 1 times negative 1, which is positive 1. So we'll get plus 3 times 3. So the answer is 13. So what's so special about that? Well, the number, the original number, is a complex number. The complex conjugate is a complex number, but when you multiply them together, you get a real number. This is used for if you're trying to simplify a complex number that has a complex denominator. And typically you want to have a real denominator, so you can use this property, multiply the denominator by the complex conjugate and the numerator by the same complex conjugate. So let's go back before we move on. Let's just make some examples here. So let's say I have one complex number, which is 2 minus 4i, so that's 1. I'll put that in parentheses. And a second complex number, which is going to be 4 plus 7i. So if I want to add those two numbers together, the answer is going to be, I add the real parts together. So you get negative 2 plus 4, which is going to be plus 2. And then you've got negative 4 plus 7, which is plus 3. And that's the I part. So that's how complex addition works. Now let's say we subtract instead of add. So let's subtract the second number. So again, we're going to deal with the complex parts, the real parts first. So you got negative 2 minus 4, that's negative 6. And then we have negative 4 minus 7. Negative 4 minus 7 is negative 11. So that would be the result for complex addition and subtraction using that example. Now if we multiply these two together, you could use this, we could plug these in, but really I think FOIL is something we're used to using. So we'd have negative 2 times 4, that's negative 8. So that's first. Inner, negative 4 times 4, it's negative 16. But we have this I, so negative 4 times 4 times the I. Then you do the outer, you've got negative 2 times positive 7. Negative 2 times positive 7, that's negative 14. I. And then you've got the last. So you got negative 4 times 7, just negative 28. And then you have I squared. So we multiply the real coefficients together. But I squared is negative 1. So you'll have negative 8 minus, let's combine these two together, which is negative 30i. And here we'll have plus 28, because we have a negative times a negative. So 28 minus 8 is 20 minus 30i. So that's how we do. complex multiplication. Now division, so here's division. So the question is, what does it mean by doing division? Well, it's not like we normally do division. And what we do is, really what we're trying to do is we're trying to convert this to a real number. So what I'm going to do is put these in parentheses so we can think of it as multiplication of first order factor kind of thing. So because we're trying to make this become, the denominator become real, we're going to take the complex conjugate of the denominator and we'll multiply both the numerator and the denominator by that complex conjugate, because that's 1. So by multiplying by this, I'm not changing the value. So in the numerator, using FOIL, I'm going to have 3 times 3, which is 9. I'm going to have plus 3i, and then outer is going to be plus 3i, and then I'm going to have I squared. And then the denominator, I'm going to have 3 times 3, which is 9. Now, because I'm using the complex conjugate, the imaginary parts drop out. So I'm just going to put those, just say it's 0. So this times that plus this times that equals 0. And then you have minus negative times positive I squared. So then what we can do is convert I squared to negative 1 in both the numerator and the denominator. And in the denominator, it's minus. So let's make sure I do that right. So I got minus because I've got negative I times positive I, so that's negative I squared. So we got to make sure this is negative. So we get negative 1. So by combining the real parts together, we'll have 8 plus 6i divided by 10. 9 minus the negative 1, which is 9 plus 1. And at this point, you want to see if there's any way to simplify it. This is our common factor, which there is, which is 2. So I divide every term by 2. So I get 4 plus 3i over 5. So that's the answer. So that's what 3i divided by 3 minus I, 3 plus I, is equivalent to that. Okay, so here's another example. Again, it's a division. So I'm going to put these parentheses here. We're going to multiply it by the complex conjugate of the denominator, both in the numerator and the denominator. So in the numerator, we're going to have 6 times 1, which is 6. FOIL, F-I-O, FOIL. I guess it's F-O-I-L. Can't spell FOIL. So outer, we'd have 6 times 2i, which is 12i. Then we have inner, negative 7 times 1, so it's negative 7i. And then minus negative times positive, 7 times 2 is 14, 14i squared, all divided by 1 plus 0. Again, the 0 is when I cancel out the inner and outer products. And then you've got negative 2i times positive 2i, so that's negative 4i squared. So combining these two together, well, let's just rewrite this. It's going to be plus 14 because you're going to get I squared is negative 1. Negative 1 times negative 14 is positive 14. Okay, so now what we can do is 6 plus 14 is 20. That's the real part. The imaginary part is 12 minus 7. So that's minus 5i. And then in the denominator, you've got 1 plus 0 minus 4 times negative 1. I squared is negative 1, so you get 5 plus 4. Negative 4 times negative 1 is positive 4, so that's 5. And then finally, look for a common factor. So you can see 5 is a common factor. So we'll get 4 minus I over 1, or just 4 minus I. Okay, so that's complex addition, subtraction, multiplication, division. So now what we're going to do is look at the complex solutions of quadratic equations. Now, do complex solutions help us plot the graph? And the answer is no, because complex solutions are not real. So you can't plot imaginary stuff on a real graph. But sometimes complex solutions are important, even if they're not real. So here's an example. X squared plus 4x plus 8 equals 0. So the question is, what are the zeros? Now we can't say we can say what are the factors, we can say what are the zeros, we can't say what are the x-intercepts, because it turns out to be an x-intercept, it has to be real. So if we take this and we use completing the square, we get to that. How does that happen? Well, you got x squared plus 4x plus 8. So you take this coefficient, 4, divided by 2, square it. So that's 4 over 2, which is 2. 2 squared is 4. So we add 4. That means we've got to subtract 4 there. Now this can be then rewritten as a as a complete square. And then this can be written as just a number. Okay, so there we go. That's how we got. I wonder why that's negative. Yeah, it doesn't make sense. It should be positive. So if we solve for x, what you would normally do is you would subtract 4 from both sides. And at this point you say, oh, I quit because I can't take the square root of a negative number. But now you can. So if we take the square root of both sides, what we'll get is the square root of negative 4. So a plus or minus the square root of negative 4. So you can break that into two parts. You can have the square root of 4 times the square root of negative 1. As long as the product of these two is that, it's the same. Now, don't write this down, but this, we could say it's the square root of 2 times the square root of 2, or negative 2. So there's different ways you could do this. This one makes more sense because I have separated negative 1 by itself, and that's I. Whereas here it wouldn't be quite as obvious, so that's why we wouldn't do that, but just showing you the properties of square roots. Okay, so then what you do is you replace the square root of 4 with 2, and the square root of negative 1 with I. Okay, so we get is x plus 2 equals plus or minus 2i. Subtract 2 from both sides to solve for x. You get negative 2 plus or minus 2i. So you've got two solutions. One is x equals negative 2 plus 2i, and x equals negative 2 minus 2i. And if I were to multiply these together, negative 2 plus, well, yeah, so how would I show this as a factored expression? Well, you'd have x, let's kind of go backwards one step just so you, normally we have this, a factor, and then we solve for x, but in this case I've got x. To get back to the appropriate factor, what I would do is I would take this term, we'll put in parentheses, and I'd move it to the other side, which means that the whole thing would become negative. And that equals 0. So if I apply the negative here, I'll get x plus 2 minus 2i. I'm going to put that in parentheses, equals 0. And I can do that with the second term as well. So x is equal to, put in parentheses, negative 2 minus 2i. So if I again put the negative sign out front, I'll get negative 2 minus 2i equals 0. and then I apply the negative sign. So you get x plus 2 plus 2i. Put that in parentheses, so that equals 0. So what I can do now is I'll have x plus 2 minus 2i times x plus 2 plus 2i equals this original quadratic equation. It's going to be equal to x squared plus 4x plus 8. And that equals 0 based on the original expression. So you take the original quadratic equation, use completing the square to write it as a complete square, solve for x. When you take the square root of a negative number, you're going to end up with this I term. So you get the final solution, x equals negative 2 plus minus 2i. Those are the zeros, not the zeros, but the solutions. To get the factors, you have to move this to the other side and then distribute the negative sign to each term. So just to show you that this works, if I were to now multiply, if I wanted to multiply this out, I'd have FOIL f first times first, so that's x squared. Then you have x times, so you have plus x times 2i, so this is the outside. X times 2 plus 2i. Inside you're going to have plus x times 2 minus 2i. And then last is going to be 2 minus 2i times 2 plus 2i. So the first term stays the same. You'll have 2 times x plus 2i times x. I get 2, I'll say 2xi. And then we have the second one, which is plus 2x, 2 times x minus 2xi. So that's just multiplying these two out, and then you can use FOIL on this part. So you'll end up with 2 times 2, which is 4. Notice this is a complex conjugate. These are complex conjugates, so this times that plus this times that goes to 0. And then the last one is going to be 2 times 2 times negative 1, and then you have I squared. So finally, these cancel out. So x plus 2x plus 2x, that's 4x. And then here, we're going to have 4, this 4, minus 4 times negative 1. I squared is negative 1. And finally, get 4x plus 8, because negative 4 times negative 1 is positive 4. 4 plus 4 is 8. So there you go, check. So it's a little, doing this multiplying out just to confirm is not trivial. And usually you can make a mistake. And notice this is the plot of the function. There are no x-intercepts. That's why we have complex roots, complex zeros.